We begin with the word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and your creation. Just pray that you'd be glorified at what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So, a couple things to mention. First of all, I think that I'm probably being slightly too rough on my notes. Like, I think the thing I got confused about last time is fine. I was just having trouble visualizing minus 90 degrees in my picture, but if you can visualize plus and minus 90 degrees in that picture, you will see that that would mean that the line segment was like a very long line of current. And the long story short there is that we derive the magnetic field for a very long line of current is what we got from Ampere's law, right? Which I'll review again. So if you have a very long line of current, right? Say I. And then you draw an Amperian loop around that, right? Like so. And, you know, so radius being r. Then the thing is, by the Biot-Savart law, we know that the direction of the magnetic field that encircles the current, right? So like we've got magnetic field going like that, and this is behind. So this would be like in front of board, and this back here would be behind the board. All right, just to, I know it's hard to judge. If I draw the picture dead on, so if I just draw the current coming out at me, right, then the Amperian loop would look like this. All right, it's easier to picture like that, and so this distance would be r, right? And the direction of the magnetic field lines is like this, right? So if I was to draw the little magnetic fields, they're like, you know, like here and like here and here and here and so forth and so on, right? So in that case, Ampere's law says that the integral around the loop of the magnetic field, which is also known as the circulation, is equal to mu naught times the enclosed current. All right? But in this case, the enclosed current is just I, and this line integral is just b times the length, which is 2 pi r. All right? The enclosed current is just I, so we find the magnetic field is mu naught I divided by 2 pi r. All right? So that's the formula for the magnetic field for a very long line of current, right? This is probably the most important formula for a magnetic field in terms of a specific example, all right? Let's see here, so example 1, let's see. So here's y, here's x, and we'll imagine that we have a current going, oh, I don't know, into the page right here, all right? And we'll say 3.0 amps, all right? A current of 3.0 amps into the page right there. Now I can ask the question, this is a very long line current, all right? So here's a couple questions we could ask. We could ask, like, what's the magnitude and direction of the magnetic field at various different points? Let's do it for 2 different points, all right? So one point, we could figure out what's the magnetic field's magnitude and direction right here. And then we'll also do it, like, over here, I guess. I do need to tell you where that current is, right? I may have said it in words, but I forgot what I said. So I'll figure that out. Let's put this where? At. Let's put it at 2, 2 in meters, all right? And I want to figure out what's the magnetic field due to that current, magnitude and direction in terms of standard angle at this point and also at this point over here. And so the points I have in mind are, let's say, this one here, it's going to be what? This is going to be, let's say, 0, 2. And this one over here will make, oh, I don't know, 6, 0. So again, the question is to find the magnitude and standard angle for the magnetic field due to this very long line current at those points. All right? So let's figure it out. For the first problem, we'll do the easy one first, this one here, right? So what's the, this is my R, let me call it R1. What's that distance? R1 is equal to 2 meters, right? The magnitude of the magnetic field is mu naught I over 2 pi R1, which in this case is, what was our mu naught? What was it, 4 pi? Tesla, -7th, okay, well. All right, that would probably be, I better get that straight, right? So that times 3.0 amps, and then I got to divide by 2 pi times 2 meters, right? Actually, let me drop the amps and the meters here. I know if I work in amps and meters, oh, fine. Let me. You told me the units a second ago here. What were they? They were Tesla meters per ampere. Let me write it out. We'll see the units cancel out. Tesla meters per ampere, and then we're multiplying by 3.0 amps or amperes. And down here we've got 2 meters, yeah? So if you look at that, you can see that the, well, the pi's cancel, and of course the meters cancel, the amps cancel, you're just left with Teslas, which makes sense. And so what's the magnitude here? What's that? Oh, I don't need a calculator for that? Uh-oh. Oh, no. Thank you for saving me that embarrassment. 4 divided by 4 is 1. Pi divided by pi is 1. Oh, yeah. So 3.0 times 10 to the minus 7 Teslas, right? Which we could also write as like, I don't know, what, 300 nanoteslas? Or if you like, 0.3 microteslas. I don't know. What are you guys a fan club of? I mean, what's your favorite multiplier? Pico? That's just weird. Dang it. What? 30? Well, I think 30?
Wait, no. We need to go 2 more decimal places.
I think it's 300. I mean, I could write it out. Here's the dumbest way to write our answer. 0, 0, 0, 0, 0, 3, 0, 0 Teslas. So there's 3, 3. Oh, wait a minute. Ah! Did I do that wrong? Oh, 10 to the minus 7. That puts the 3 here, doesn't it? Yeah. Duh. 6, 7, yeah. So yeah, it's 300 nanoteslas. All right, let me stop this. Who cares? All right. Okay. I mean, I'm only going to make like a 30% deduction if you get that wrong anyway, right? So come on. Just joking. It's only 20%. But sorry, I'm recycling my jokes now. But so that's the magnitude. What's the direction? Can we draw a picture? First of all, do we need to use the cross product of 3-dimensional vectors to do this? We do not. You can, but you don't need to, right? You should be able to use the right-hand rule and some just plain old reasoning. So we go, you know, it's going, which way is it going? It's going into the board, right? I got to point my thumb in the direction of the current. Then my right hand will encircle in the way, so the magnetic field lines wrap around like this. So when they come up here, they're going up. So my magnetic field line is going, it has to be tangential to the, so that's B1. So what's my standard angle there? Theta equals to what? I heard a 90? I'll take it. Let me call that theta 1. Let me call this B1 for part A. All right. Are we so far so good? Okay, so if we look at the other you know, point over here, and that's my R2, let me talk about the direction first. What's the direction of the magnetic field? See, it has to be perpendicular to the radius. It's like this. What's the standard angle there? I have no idea, but I need to work it out though, right? So like, and if we look at this triangle here, right? What are these distances? We got what? We got a 6 here and a 2 there, right? In meters. 4? Why did I have a 4? Oh, because I can't do math. Okay, yeah, so 6 minus 2 is 4. Thank you. That's better. Of course, those are both in meters. So what's R2 equal to? Square root of 20 meters. But we like decimals in here, so if we get 4.472. Something like that, right? So for part B, we've got, you know, B2 is mu naught I over 2 pi R2, which is 4 pi times 10 to the minus 7th times my, still 3 amps, right? Divided by 2 pi times my 4.472, and that's all, of course, going to be in Teslas. Whatever that works out to, right? That, I think, in good conscience, I can use a calculator for. So that inverse times 3 times 2, I think 1.342 times 10 to the minus 7 Teslas. Or if you like, you know, well, I mean, you know what? That's a perfectly good way to leave the answer, and I'm going to do that. Enough of these multipliers. I'm tired of them for the moment. My bad. So what's the angle? So if this is beta, right, then this here is 90 minus beta, right? Which makes this beta again up here, right? So I can find that reference angle off the axis by, like, beta is what? Inverse tangent of 2, thank you. So that's a what? Whoa, I'm in radian mode. That is not helpful. Let's try this again. Radian mode. Who's been using my calculator? So here, 63.43 degrees. Now, I'm not saying that's the answer. I'm just saying that that's relevant to the answer, right? So that's the angle here, right? So at theta equals to what then, guys? Theta 2 equal to what? 243.43. Very good. Why is that? Does that make sense to you guys? The angle, the magnetic field's pointing this way, right? So it's decidedly in quadrant what, 3? So it should have an angle between 180 and 270, yeah, for the standard angle. For these problems, it's important that you understand what's being asked. I'm asking you for the standard angle of the magnetic field. I'm not asking you for the standard angle of where the magnetic field's being measured. That is a separate and less interesting question, all right? I mean, what's the standard angle of this point? 0. What's the standard angle of this point? 90 degrees. Just happens to match up there, doesn't it? Oops. But this can happen. They don't have to not be equal, but they're usually not equal. Any questions? All right, well, if you understood this example, one of your homework problems should be like stupidly trivial now. Another example. So now that we have the formula for the magnetic field of a very long current, we can go back and do, I did some examples before qualitatively, we can now do them quantitatively, right? For example, we can have a current I1, let's say going up like this, and we can have a current I2 going up like that. We can, I'm going to take a break from numbers here and just do things symbolically for a bit. We can have the distance between these two, BD, right? Distance D apart. And then I can calculate what's the force per unit length of the magnetic force on the one wire due to the magnetic field created by the other wire. Do you see what I'm saying? I1, so like if we drew these like they were going into the board. So here's my I1 and here's my I2 into the board, right? I'll draw the magnetic field of I2 in the red, right? So it does like that, right? So one of them, you know, there's all these, I mean, I probably shouldn't draw so many, but anyway. So it's going into the board, right? So right-hand rule, wrap around. So going up on this side, going down on that side. So in particular, right here at this point, we've got B2, magnetic field due to current 2 in that direction, going upward, right? On the other hand, if I draw the magnetic field lines of I1, you know, like that. So again, they're going down on this side. So there's actually the magnetic field from 1 is like this here. And of course the magnetic field lines from current 1, the magnetic field will be going up on this side of I1. Right? The magnetic field encircles the current like this. But the larger point is, we can figure out what the force of the magnetic field from the second current is on the first current, and vice versa, right? Now let's do this specifically for a particular length of these currents, right? So like, let's do it for, you know, just a token from here to here, right? Length L, let's say, right? And if we calculate, like, let's work it out. What is the force? So the force on, you know, L at I1 due to B2, which would be what? This would be, remember our formula was mu naught ILB. So what's that? We have mu naught I1 L B1, no, B2, right? Make sure I haven't remembered this wrong now. Tell I cross. Now, why don't I need the cross product here? Why is it just multiplying? Force of on I1 due to 2. You notice that the magnetic field's perpendicular, right? So we do I1 crossed into B2. The force is like this, right? I'll call it F1. Force on 1. Since the magnetic field and the current are perpendicular, we just take the product of the magnitudes to get the magnitude of the cross product. But what's the other? But now what's that equal to? See, that's the thing we couldn't do before, but now we can do. So we've got mu naught I1 L. What's B2? Well, B2 is there a mu naught there? I'm sorry, all of a sudden there's no mu naught there. God, don't let me do that, guys. Come on. Dudes. No. What's the Lorentz force law in terms of current? It's just ILB. So we had I1 LB2, right? Which is equal to I1 L times mu naught I2 divided by 2 pi, the distance between, right? What's the distance? D. The distance is D. That's the distance between where the current is generating the magnetic field and where we're measuring the magnetic field over here on current 1. Which I'm going to just clean up a bit because I really like to write this mu naught, I1, I2 divided by 2 pi d times L. All right. But likewise, right? What's F2? Force on L at I2 due to B1. So it's the same silly calculation with 1 and 2 flipped around, right? And it works out to mu naught I1, I2 divided by 2 pi d times L. Of course they're equal, right? But what's the difference? There is a significant difference. Direction, right? So F1 is that way, and F1 is to the right in my picture, and F2 is to the left in my picture, right? If I draw it on the above picture, F1's like this, F2 is like that. They're equal but opposite. But so, like I was telling you qualitatively last class, parallel currents attract each other, right? But I didn't have a formula for how much. We could just see the direction last time. But now I can tell you that F1 over L equals to F2 over L. This is the force per unit length, right? And apparently it's mu naught I1, I2 divided by 2 pi d. There you go. And my apologies, I may have just worked one of your homework problems, but I think it's for the best. All right. So, any questions? No questions. Okay.
You mentioned the cross product.
Uh-huh.
When do you do the cross product?
When we need to, of course. I mean, when do we do the cross product? When does it? So you're asking me to come up with an example where the cross product was an inevitability, like I can't help it but to do the cross product. Sure. No. That's a good question. That's a good question. Example 3. I do not reject your question. Not at all. So here's one. Suppose I have a line with direction vector 1, 2, 3 direction, right? With current I equals to, I don't know, 23 amps. There we go. Okay. Then So this is a steady current, steady current, long wire, right? And I'm assuming it goes through the origin. So like here's a point on that line. Okay. Then, I don't know. I could ask any number of annoying questions, I suppose. Like, how about, what's the magnetic field here? We call that P. Find the magnetic field at P. I won't ask you for the standard angle this time because it's a three-dimensional vector, right? Although I guess I'm not going to use the, probably not going to use the cross, I don't know if I'm going to use the cross product or not here. I don't know, man. I don't know. The ones that most naturally use the cross product are like just straight Lorentz force law questions, like problem 1 on your homeworks like that. Because I just straight give you velocity, magnetic field, electric field, and like the charge. So you just calculate V cross B for the Lorentz force. So that's a place. See this, I know what happens here, right? So the Ampere's law thing that we led off class with today still applies here, right? Like it's still the case that the magnetic field has to encircle the wire, right? But then I'm left with questions of geometry, right? Which are maybe not too easy for some of us. Certainly for me on any given number of days. Like, okay, so I guess I need to tell you, oh, in the 1, 2, 3 direction, which let's say is this way, right? So, you know, wait a minute. Oops. Let me draw it like that. Maybe that should be unambiguous. So they're encircling like that. So the question is, what's the distance from here to here? How far is it from the point 070 to the line? How do you figure that out? A projection. Project where? Project what where? I like it. A line onto the y-axis. Ooh, I like that. How about I flip that around? How about I project the y-axis onto the line? I think that might work. That's a good idea. So if what's this vector here? Let's give this name. This thing a name here. This is, well, it's P. Actually, it's the P vector, isn't it? Notice that what we're doing right now would have to be modified if the current didn't go through the origin. If the current didn't go through the origin, you need to pick a point on the line in which the current's flowing and base your argument off that point, something like that. But this animal right up here, if I can use this hideous Carolina blue marker, this character right here is what we would call the projection. Let me call this thing U. The projection into the U vector direction of the point P. What's the formula for that? How do you calculate the projection in the U direction of the point P? Well, you take P, you dot it with the U unit vector U, and you multiply by U hat, right? which in this particular case is, what the formula for that is the, you do 0, 7, 0, dotted with 1, 2, 3. You divide by, you know, the 1, 2, 3, dot 1, 2, 3, and you put that in the 1, 2, 3 direction. So here's a formula for the projection, if you don't want to calculate the unit vector. And that is 14 divided by, this is in meters, by the way. 1 plus 4 is 5, 5 plus 14. Wait, what? Dudes. No way. Oh, that's weird. Way? All right, way. So, yeah, that happened. That just happened. Whoa, that's cool. That is such an accident. So, wow. So my picture is like right. I guess. I mean, well, anyway, that is the 1, 2, 3 vector in the Carolina blue. What does that make R? Well, the length of R, all right. Well, I haven't given a name for that thing, but the length of the, I usually call it orth, U of p. So this is the vector. The length of the orth vector is R, and that is the length of p minus the projection. See, you can always decompose a vector as a piece that's parallel to an axis plus a piece which is perpendicular to the axis. The perpendicular piece you simply get by the subtraction of the parallel piece off the vector. And so here that works out to what? The length of what? 0, 0, 7, my bad, 0, 7, 0 minus 1, 2, 3. Man, this is cool. It's got no fractions in it. I should have made this a test question. It's not too late? Okay, well, thank you. Keep that in mind. Minus 1. Troy's like, what have I done? What have I done? I should have just been quiet. I should just kept quiet. What's wrong with me? Let's see here. Troy will be in the hallway for his beating after class. Let's see here. This is 25, 26, 26 plus 9, 35? Can we make it 36? That would make it nicer, but no. It's squared 35, apparently, meters. So there you go. All right. Lovely. Actually, I really should have calculated orth. Well, this is orth, right? This is the orth right here. So the magnitude of B, we got it. Mu naught I over 2 pi r, which is apparently, well, I don't want to write the numbers down. I just want to calculate them. So we got the square root of 35 and I. Let's work it out. What we got? So we're supposed to do what? 4 times, what was my 23? Divided by 2, divided by square root of 35, I think. Oh man, cube root, no. What? Man, stupid calculator. Oh, cool. I believe I get 7.775 times 10 to the minus 7 Teslas. Am I right? Anybody else get that? Now what's the direction vector though? What direction does the magnetic field go at P? I mean, you can kind of visualize it, right? It's like, maybe I can't visualize it. It's, anyway, it's, come on. So the magnetic field at this point P, right? It has to be perpendicular to what? This vector, and also the direction vector to the line, which is, I'm going to graph it like this, which is just my made up picture for it. I don't really know. But I can figure it out because the direction of B, so B has to be parallel to the cross product of what? 1, 2, 3, and what? I want a vector which is perpendicular to both the direction vector of the line and this guy. Because that's the vector which is going from the closest point on the line to the field point. That's the radial vector. The magnetic field must be perpendicular to the radial vector off the axis of the current and the direction vector of the current, which is that. So hopefully I've got the direction right. I got to think about that for a second, guys. Oof. Well, 50-50, right? I'm sorry, I think I'm going to have to leave a plus minus here because I'm not 100% sure without drawing some more pictures, and I'm kind of tired of this example at the moment. So it should be perpendicular. It should be parallel to that vector. So you asked me at the start of this, like, where can the cross product come up? But it comes up in the need for the cross product comes up in problems where we can't necessarily just draw a simple picture to understand the direction of perpendicular things. That's what I use it for anyway when I'm pushed into a corner like this here.
But on the test, it would probably just be problems related to problem 1.
Oh, like on the test, yeah, we can bring this back. I mean, sure. Thank you very much. All right, I digress. Where are we? Okay. So I wanted to talk to you a couple minutes today about Ampere's law and about its differential form. So I'm going to use I guess I don't need to use the projector for that. Just give me a second here. Just got to remind myself what I was going to say. All right, so let's talk about Gauss's law and Ampere's law and all this. I told you guys before about Gauss's law. Of course, we have Gauss's law in integral form, and we have Gauss's law in differential form. Do you remember that? I don't know if you remember or not, but let me remind you. So we have on the one hand, the electric flux, right, is equal to charge enclosed divided by epsilon naught, right? And so that is directly the integral of the electric field over the surface, right? And that surface, say, whatever, say the surface, right? And that's equal to Q enclosed over epsilon naught. Of course, that we can also write as the triple integral. And so this S is the boundary of some volume, let's call it V. So the triple integral over the volume V, I'll bring my epsilon naught out here, and then we have, like dq dv times dv, right? And we usually write rho is equal to dq dv for the charge density, right? Remember that? And so there's this beautiful theorem of calculus 3 that you'll soon learn, that this is actually equal to the triple integral of the divergence of the electric field over the volume, right? And so, lo and behold, if this is equal to that for arbitrary volumes, it stands to reason that there's a differential relation, in particular that the divergence of the electric field is equal to the charge density divided by epsilon naught. So this right here is Gauss's law in differential form. So we talked about this briefly before. I don't think I really ever tested on it or anything, but there it is. Natural question to ask, what about magnetic fields? Right? If I look at a closed surface, what's the flux of a magnetic field? How do so let's think about this. Like, here's let me think about a cube. Cubes are easy to picture, right? And suppose I've got some currents, like here, What's the magnetic field do? What's it do? Think about it. It comes in here, right? And it goes out the other side, right? In and out. In and out. In and out, right? If I imagined another, magnetic field like right here, it's easier to picture, coming out at us, my field lines so what I'm trying to picture, and I'm not doing very successful, like suppose just let me get rid of this one. It's counter to my purposes. You should be able to see, right, that if I think about it piercing the cube right here, let's say, so here this is inside the cube, then it comes back over here, right? If you have a better ability to visualize than I do, you can convince yourself, because magnetic field lines always come in loops around currents, what's the magnetic flux through this cube? Yeah, the magnetic flux is 0. So magnetic flux would be the surface integral of BDS, all right, over some, the boundary of some volume. And the divergence theorem again applies. That's the divergence of the magnetic field integrated with the volume, right? And since that holds for arbitrary volumes, this goes to show you that apparently the magnetic field is a field such that its divergence is 0. So like, as we talked about a little bit, the magnetic field always comes in dipole patterns. That's the least complicated pattern possible, is the dipole pattern. Like it does these loops, or the circles around the thing. But the point is that whatever you think, all of the physically observed magnetic field patterns have this property that they don't diverge from a point. If you could find a magnetic field that actually had a non-zero divergence, that would speak to the existence of something called a magnetic monopole. So a magnetic monopole would be analogous of, electric charge, but for magnetism. It is, so far, an experimentally determined fact that there do not exist any magnetic monopoles. However, there's very interesting theoretical things that come from the existence of a magnetic monopole. For example, quantum mechanically, you can argue if there exists even one magnetic monopole, then charge must be quantized. That is to say that charge has to come in integer multiples of some fundamental unit. We observe this in nature. Every charge that's measured is an integer multiple of the electron charge, positive or negative. There are quarks that have fractional charges, but none of those can be observed directly because they are subject to something called quark confinement, which is something that's designed into the theory because we've given up on the hope of finding fractional charges in any experiment. All right? So it seems to be a fundamental law of nature that charge has to be found in integer multiples of the electron charge. So you can see if that's a straightforward consequence of like quantum mechanics and the existence of a single magnetic monopole, why you'd like to believe there is such a thing. Because we do observe charges quantized, and yet these are not observed. All right? So I think that's kind of neat. And so this is sometimes called the no magnetic monopoles equation. It's not something we ever calculate anything with, but there it is. Now, the other thing we have been doing, though, is recently we've been saying what? The integral of the magnetic field dot dl, right, over some loop, right? So let's call that loop the boundary of a surface. We said that that's equal to mu naught times I enclosed. All right? So another way to write the enclosed current is mu naught times the integral over the surface, all right, of the current density dotted with the surface area vector. So J is the current per unit area. J is called the current density. Last time we looked at a problem where the current density was uniform. We had a uniform current density in a solid wire. And we used Ampere's law to figure out the magnetic field was 0 at the middle, out to its maximum value at the edge. That was an example of uniform current density. You could consider currents which don't have a uniform density, but in fact have some actual dependence on where you are in the surface, where your current's cutting through the surface, right? So let me tell you something else that you haven't yet experienced in Calculus 3, but you will soon experience if you're in there, relatively soon. There is yet another theorem that involves these vector calculus integrals, and that's that the integral around the boundary of the surface is equal to the integral of the curl of the vector field over the flux of the curl, you could say. The flux of the curl through the surface. Now, so if this is equal to that for arbitrary surfaces, then this gives us the differential form of Ampere's law. The differential form of Ampere's law is as follows. It's the curl of the magnetic field is equal to mu naught times the current density. So this is the analog of, it's sort of kind of the analog of Gauss's law, but for magnetism. But here again, the current density. Now this is a special case of the general law. This assumes that the currents are steady, that the currents aren't changing with time, or at least that the change in time of the current is so, it's negligible enough that we can ignore it, all right? When the current changes in time, when it's not a steady current, other considerations come into play. We'll talk about those later in the course. But anyway, this is the differential form of Ampere's law. Anyway, so next time we'll do more Ampere's law examples. Sorry, I was going to do another example today, but you guys had a really good question, which has got me thinking about the next test, so I do appreciate it. So.